So now let's take a look at the third piece of information we're going to process from H NMR. And in this case, this is the splitting or multiplicity. So and this is one that usually takes students the most time to kind of assimilate out of all the three pieces of information here. But the splitting or multiplicity indicates the number of neighboring hydrogen atoms. So we got to talk about what this means here for a second. But neighboring hydrogen atoms here, so are non-equivalent hydrogen atoms that are 3 bonds or less. That's the important part here. 3 bonds or less from the hydrogen you're actually examining. Most of the time this means that the neighbors are hydrogens attached to the adjacent carbons. And the idea is that hydrogens attached to the same carbon are actually 2 bonds away, but because they're typically equivalent in most cases, due to free rotation, they don't end up causing any splitting. Now, if hydrogens attached to the same carbon are not equivalent, as sometimes occurs, like with alkenes or on a ring or something like that, then they definitely will split each other. But most of the time, neighbors are going to be these hydrogens on adjacent carbons that'll cause this splitting. And it just ends up being a difference in hydrogens being in alpha versus beta states, and then all the different possibilities that are there and stuff like that. That's what ends up causing this splitting and altering the environment, or at least possible environments, to a few different, slightly different environments that are possible. So we look back here again. We've got these 3 hydrogens that are equivalent, and let's take a look at them first. So they're attached to this carbon. This is the adjacent carbon here, and there's 2 hydrogens attached there, and these 2 hydrogens would be the neighbors for the 3 of the methyl group. And so these 3 hydrogens over here, we'd say, have 2 neighbors. So in having 2 neighbors, the neighbors plus 1 rule, you take the number of neighbors 2 plus 1 to get 3 peaks, and 3 peaks we'd refer to as a triplet. So the integration we dealt with last time tells you how many hydrogens you have in an environment, but this splitting or multiplicity tells you how many hydrogens are nearby. So we get something about the immediate environment as well as what's right around it. And H NMR is super powerful for putting together. So it's pretty much the most powerful technique we have at our disposal in organic chemistry for putting together the structure of a molecule. So let's take a look down the chain here. So at these 2 hydrogens again live on this carbon. There are 2 adjacent carbons. So in this case, no hydrogens live on this carbon. But there's 3 hydrogens living on this one. So we say that these 2 hydrogens have 3 neighbors. So in having 3 neighbors, the neighbors plus 1 rule would get us 4 peaks, and we call that a quartet. Cool. So you have like singlet, doublet, triplet, quartet, quintet, or pentet, depending who you talk to. Sextet, septet, so on and so forth. And oftentimes when we start getting big numbers that are hard to distinguish and stuff, some people just throw the word multiplet around there, but we'll see that's actually got a specific definition associated with it. But typically once you get up to 7 neighbors, that's about as high a number as you'll normally see until we just start having some funky splitting we'll talk about towards the end of this chapter. In this case, last but not least, we've got this OH hydrogen. And we'll find out that OHs and NHs typically don't undergo splitting. Now, in the case of the OH, it's due to what we call fast proton transfer. So it turns out with fast proton transfer, this H is acidic enough that it's probably just being exchanged with other molecules or even with the solvent, potentially. And as a result, there's not just one environment. There's a whole host of average environments it's going through as it's being exchanged. And this exchange process is fairly fast, faster than the time scale of NMR. And so what we're going to see is a big average of environments, 1, so they often show up as broad singlets. And 2, one of the side effects of this is that also they typically don't end up being anybody's neighbor and nobody's their neighbor as well. So they often show up as singlets and don't cause any splitting for nearby hydrogens either. Now, if you've got a really pure sample where this fast proton transfer is not occurring, you can see splitting with this. As an undergraduate, you're very unlikely to see it, but I have seen it show up on rare occasions in an undergraduate class during the last 20 years. So I can't say it'll never happen, but it probably will never happen for most of you. So now let's take a second look at that spectrum for propionic acid here. And we just a second ago said these 3 hydrogens have those 2 hydrogens as neighbors, and the neighbors plus 1 rule leads to 3 peaks, so they're going to show up as a triplet. And indeed, they do show up as a triplet. And then we said that these 2 hydrogens here have these 3 hydrogens over here as neighbors, and therefore they're going to show up with 4 peaks, a quartet. And there indeed is that signal. You can count the peaks, 1, 2, 3, 4. And then finally we said this OH is probably going to show up as a broad singlet, and that is indeed what we see. So we can take and match up again exactly what we just predicted with the actual spectrum.